This is Unit 3, Topic 7, Creating a Confidence Interval for a Population Mean. You'll find that there are a lot of similarities in creating confidence intervals for the different parameters. In the last topic, we looked at creating a confidence interval for a population proportion. In this topic, we're going to be creating confidence intervals for population means. As you can see on the excerpt from the confidence interval reference tables, there are two cases for estimating a population mean. The first case is if you have the population standard deviation sigma. This is very specific and doesn't really happen very often, but it's going to link well to what we already know. The second case is more realistic, and it's if we have the sample standard deviation S. Either way, we have a standard deviation. It just matters which standard deviation we end up having. If the population standard deviation is given to you, it's usually going to be pretty obvious. I always say in class that they punch you in the face with it. They're going to have to be very, very blatant that it is a population standard deviation because it is going to kind of come out of nowhere. The sample standard deviation isn't always going to be so obvious, and very often you will have to calculate the sample standard deviation yourself using Stata. So the first component is the point estimate, and the sample mean x bar is the point estimate for the population mean. So think about it, if you want to estimate the population mean, and we have a bunch of sample data, the sample mean is going to be the best guess for the population mean if we've done a good job with our sample. Next, we have three assumptions that are pretty much the same for each case. They differ in this last item, which really isn't an assumption. It's just more of to help decide which case that we use. So first, the mean needs to be normally distributed. So this is the mean of our sample. Now, by the central limit theorem, if the sample size is at least 30, we know that we can assume that the sample is normally distributed. Or the population could be known to be normally distributed, or you can perform a Shapiro-Wilk test of normality in Stata. The last few examples will cover that, but for now we're going to put the testing for normality stuff aside. Next, the sample must be random. So again, in the real world, not a lot of samples are actually randomly distributed. They very often are close to being well-behaved enough to be considered random, but they aren't often randomly distributed because we don't always have a nice list of our population. So this will pass if the problem says random. If it fails, you're going to exit out, but you're still going to keep on going. So that will happen occasionally, but usually I'll make it look like the assumptions will pass almost always. The third item here is just basically asking you what kind of standard deviation that you have. So remember, sigma is the population standard deviation. So if you know sigma, then you're going to use the z distribution, which is the regular old bell curve, and these formulas for finding a confidence interval. If you do not have the population standard deviation, the t distribution is the distribution that the values will follow, the means will follow. And then you'll end up using these formulas down here. Now, the only difference that you'll see between these is that the critical value is t instead of c, and the standard deviation is the sample instead of the population standard deviation. So there are a few sections of notes coming up. They're probably going to recover a little bit of what we just said, but in general in class I usually just go over this one little table, and then the notes are more for student reading, but we'll talk about them a little bit. So again, there's two cases, which depends on what type of standard deviation you have. If you have a population standard deviation, you really have a lot of information about your sample. So for that reason, you're going to use the z distribution, which is more precise and tight towards the middle of the curve. If the population standard deviation is not known or given, then you're going to use the t distribution, which is a lazy version of the normal distribution, is kind of what I call it. It's just heavier in the tails. So here are some steps to using the t-tables. I'm actually going to skip this because we are just going to use the t-tables throughout the practice here. We're going to use it for our second example. This last bullet is the only one that I want to emphasize, however. So the t-tables are going to require us to look up a sample size. And if the sample size isn't in the table, you're going to go down to the lower value. You're never going to go up. Going up is going to basically be lying about how accurate your sample is. Because if you go up in the sample sizes, you're going to say that you have a bigger sample that you actually don't have. Other than that, we'll go through these specifically once we get a table popping up. So again, a reminder that the Z and the T distribution are very similar. And besides the fact that the T is more of a lazy version of the Z distribution, your instincts for the normal distribution will still apply. So we have positive t-scores above the mean in the middle, negative t-scores below the mean, when the mean would be, of course, in the middle. So I recommend, again, always trying to ask yourself, do your answers make sense? And, instead of just using the table and getting some values out and putting them on your paper. So one of the things that you will need for using the t-tables are degrees of freedom. We mentioned degrees of freedom briefly in topic 5. Degrees of freedom are actually pretty complicated, but the simplest way is that it's just one less than the sample size. The technical version is on the slide here. So basically we take into account the number of pieces of information we have versus how many parameters we have, and we perform a subtraction of the two. Another way that you can think of this is that if you were to infringe some kind of requirement or some kind of stricter criteria onto your data set, you may need to throw out one of your values. But in general, degrees of freedom is just one less than your sample size. So just the last reminder, how we test for normality is using the Shapiro-Wilk test for normality in SATA. So if your sample size is less than 30, this is the only time you're going to have to test for normality, because otherwise the central limit theorem is going to apply. So we will talk about the Shapiro-Wilk test for normality again very briefly, but what it boils down to is that the output of the Shapiro-Wilk test is a p-value, which is also known as a significance value. So if your p-value is less than 0.05, you're going to fail the normality assumption. If it's greater than 0.05, you will pass the normality assumption. I will never put you in a position where this assumption fails, because if it does, you will need to use a different test. We're actually not going to go over that test. In the next class, the data analysis class, we go over the types of tests that have no assumptions. They're called non-parametric tests, and they're very bizarre how they work, but they're also very graceful in a way, I would say. So we'll talk about this a little bit, but later on we're going to do a few practice ones first. So all of the examples from this topic are real data. The Cardiac Care Network in Ontario, Canada collected information on the time between when a patient is recommended for heart surgery and when the surgery is performed. They reported the mean wait time for a random sample of 539 patients was 19 days. The population standard deviation was known to be 10 days. So the questions for this problem are, what is the best point estimate for the mean wait time? Perform an assumptions check. Find a 99% confidence interval for the mean wait time. And then lastly, there is a question regarding the results that you get. So first, the best point estimate for the mean wait time of everybody ever, we're going to assume that our sample, especially since it was randomly selected, we're going to assume that that 19 days is the best guess for the population mean. Remember, we don't have census data. They might be able to do it, but maybe it's a little bit more difficult. Maybe not all of the records are inputted in the same way, or maybe they're not, all maintained in the same way. So it's not very easy to pull all of the records at once. But we have a random sample that says 19 days, so that's what we're going to assume is our best guess for the population mean. An assumptions check. So there are 3 assumptions for this. The last one is kind of a spoiler because it's not really a true assumption. It's just helping you decide which test to use. So First, we need a normal population or a sample size of at least 30, which we have because we have a sample size of 539 patients, which is on the larger size. Random sample, we've got it. And the reason is because they say it. I know it sounds like kind of a cop-out, but that is the reason why we have a random. And then lastly, sigma, our population standard deviation, is known primarily because it tells us. So the population standard deviation is known to be 10 days. This is going to be extremely obvious when you have this case. As I mentioned before, in the real world, this doesn't happen very often, but it does connect very well to what we already know how to do. So we're going to start with one of these. So next, find a 99% confidence interval for the mean wait time for the heart surgery patients. So the first thing that I always do is I start off with my point estimate, the sample mean, and then I get my picture. So the picture isn't ever worth any points. However, it's a really solid setup and it leads you into each of the pieces very smoothly. So if we have a 99% confidence interval, we're going to have 99% of our area in the center of our distribution, which means that we have 0.5% remaining for the tails. So if you're having a hard time finding this z-score, as well as this one, I'm going to ask that you go back and review some of the topics in some of the examples in topic 5, or you can feel free to send me an email, but this is material that we had done even in the previous unit, so it's not going to be brought up again like it's new. So what you will do, however, is look up 0.005 in the table. And so when you get to that value, there are two z-scores that are equally distant from that value. 2.58 is what I use just because I know from experience that that's what it is. But if this were an exam and you use 2.57, that would be perfect as well. So now we have the pieces that we need in order to find our margin of error, which is our wiggle room. So I always rewrite the formula. I recommend doing this especially on an exam because if something goes wrong, just copying over your formula, but everything else is correct, you will get partial credit. So this right here is our critical value, which is this z-score right here that has half of alpha to its left, or right actually, which is 2.58 times the population standard deviation divided by the square root of the sample size. Now, two things that will go wrong here that have absolutely nothing to do with your skill with this problem. First of all, very often people will accidentally drop in the wrong numbers. So they'll just pull in numbers from the problem and it's just kind of more of being robotic. So you want to be careful, make sure that you double check all of your values. And then the square root of 539, what happens is this square root blends with the division sign. And many times if you do have a calculator error, it will be because you've forgotten this division right here. So once you perform this multiplication and division, you should get 1.1 days. I do put a unit on almost everything as possible just to make it make more sense in actual context. So when we construct our confidence interval, we add and subtract our wiggle room onto our best guess, 19 days. So here we get a 99% confidence interval of 17.9 to 20.1 days. So this is again the estimate for the mean wait time for heart surgery patients after being told that they need surgery. So there is a 99% chance that the confidence interval contains the true population mean. So lastly, a doctor states that the average patient waits 3 weeks before their surgery is performed. So this could be a case where maybe a doctor is presenting to the board of trustees saying, you know, hey, we need better intervention for when a patient requires heart surgery. Well, if this doctor wanted to state 3 weeks, would they be correct or not? So our confidence interval from part C does not have 3 weeks, which is 21 days inside. And even though it comes close, it doesn't have 21 inside, and we need to cut off somewhere, which is our end of our confidence interval. So the MVD is the minimum verifiable difference, the minimum difference that we say this person is wrong, which is going to be 0.9 days. So I mean, basically they're off by 1 day. But The reason we find the MVD is we don't want to just say, hey, you're wrong. We want to say, hey, you're wrong, and here's by how much. Because this doctor isn't off by very much. As a statistician working on this problem, I might say, it's upwards of 3 weeks would be, I don't know, sort of cheating, but would be more correct than saying the wait time is 3 weeks, because we've shown here that the wait time is not statistically 3 weeks. It's actually less than 3 weeks. So the next example, this is actually real data as well, and this is real. It's the solution that we get is true to the real world as well, and it's kind of surprising to some people. But in a sample of 106 randomly selected body temperatures, the mean body temperature was found to be 98.2 degrees Fahrenheit. The sample standard deviation was 0.62 degrees Fahrenheit. So the difference between example 1 and example 2 is what type of standard deviation that we have. So in example 1, we had the population standard deviation. In this case, they had some sample data and they found the mean and standard deviation and gave them to you, which is nice. So in the future, we're going to be finding our own sample data. So it's going to be a little bit more work on our end. So the same 4 questions follow. What's the best point estimate for the mean body temperature of everybody? Perform an assumptions check. Construct a 98% confidence interval estimate for the mean body temperature, and then a question that follows the confidence interval. So what is the best point estimate for the mean body temperature of all healthy humans? Well, 98.2 degrees is our only guess for the population mean, but if we have a random sample like we do in this case, it's also expected to be a good guess. Next, perform an assumptions check. First, the population needs to be normally distributed, or we need to have a sample size of at least 30, which we definitely have here with a sample size of 106. The sample must be random, which we've already discussed that we have. And then sigma, our population standard deviation, is unknown. So again, that's not really an assumption. It's more of just kind of a check of which case we have, whether we have the population standard deviation or we have the sample standard deviation, and we're going to use the t-distribution. So all 3 of these get the check. We will move forward to our confidence interval. So construct a 98% confidence interval for the mean body temperature of all healthy humans. Again, I always start with the sample mean, which is our point estimate of 98.2 days. And so here is a drawing of the picture. We have 98% in the middle. We have 1% on either end. And then that circled on the top, n-1. This is the number of degrees of freedom. So what I've pulled out down here is just part of the t-tables. The t-tables are in the folder for topic 7 as well as the statistical distributions folder, so you can find those in both locations. So we have a sample size of 106. We have 105 degrees of freedom. So we're actually going to use the 100 row. So there's no 105 here. So we always go down instead of up. So we can't preach that we had a sample size of 200, which actually be 201, because we didn't have that. We only had 106. So you can only be as strong as your weakest member here. So these top 2 rows here, they go together, they don't conflict each other. So the top row here is the area in one tail. So if you want to just look at one of these tails here, you have 1% or 0.01 inside there. This corresponds with having 2% in both tails. I'm honestly not sure why it is set up this way, but this is how almost all of them are. So you have a choice of either looking at both rows to cross-check yourself or just choosing one of them that you like the most. Either way, you should come up with 100 and this column meeting to be 2.364 for your critical value. Now, just like how the z was symmetrical along the middle, so is the t-distribution, so those instincts will still apply. So this is what your picture for this will look like. Again, the picture aren't graded portions unless they're a standalone question like they are in your learning quiz for this week. Otherwise, if you have a confidence interval question. So once we have all of this set up, Then we can go to our error formula. And the difference that we're going to find from example 1 to example 2 are we're now using the t-distribution, so we have this t-score instead of the z-score that we had previously. And then we have the sample standard deviation instead of the population standard deviation. This gets us an error of 0.142, which is degrees Fahrenheit. When we construct our confidence interval, we get 98.2 minus our error, 98.2 plus our error, which gets us a confidence interval at the 98% level of 98.058 to 98.342 degrees Fahrenheit. So there is a 98% chance that the true value of the mean body temperature falls within our confidence interval. The final question says, the average body temperature is assumed to be 98.6 degrees. What does this suggest about using 98.6 degrees as the mean body temperature? Well, we found out more recently that the mean body temperature is closer to 98.2 degrees, but comparing it to our confidence interval, we find that 98.6 degrees is not inside the confidence interval. So we decide that that is not a realistic mean temperature. So what we do say is that 98.6 minus 98.342, which is the closest number to that value, is 0.258 degrees Fahrenheit, which is MVD, which is the minimum difference that we're saying 98.6 is based on our sample data. So there are two examples that are available up on Moodle that are not covered in this PowerPoint, but I do want to talk about Stata just for a little bit. So I'm going to head over to that Moodle page. So example 3 gives us a data set. And so in order to answer these questions here, including part of the assumption check, we are going to need to use Stata. The data that we have is just a raw data set. It's not the mean and standard deviation, the summary statistics that we were given in the previous examples. So I'm going to open Stata here. So what I would do in order to answer both A as well as the normality check for B is I would enter this data into the data editor in Stata. So I'm going to pause while I do this. So just as a reminder, if your data is coming in as red, then it's not reading your variable as a numeric variable. So you can either, I would just recommend starting over, is probably the easiest. So we need to do two things with Stata. The first thing that we need to do is get some summary statistics. So in order to get the point estimate for the amount that the family spends per day at the theme park, we would need to go to our cost variable. The standard display will be okay, but I'm just used to displaying additional statistics. Let's be risky and click on the first one. So this is a mean of $193, and this is a standard deviation of 26.73. This is a sample standard deviation because you found this as the result of a sample. So the sample standard deviation means that we're going to use the t-distribution in that right side of the column. Now next, when we get down to the confidence interval, the assumption check, we need to verify normality because we only have 25 pieces of data here. So in order to verify normality, this is a throwback to Unit 1, we go to distributional plots and tests, and this is the Shapiro-Wilk normality test. So cost, okay. So the p-value for normality on this is 0.2370, which is higher than that cutoff of 0.05. So we would have the normality assumption pass here, not the sample size part of it, but it's one or the other. So as long as one of those passes, then they are both okay. So I'm going to leave the rest of the last two examples up to you. If you're having any questions, please feel free to send me an email or schedule a Skype appointment or an appointment at my office hour. It's just up to you to show your error formula and the construction of your confidence interval. So once you have this piece,